For the past century, we have been constructing a very particular understanding of reality. We call it the Standard Model. It represents humanity's greatest intellectual achievement. It describes how particles interact, how fusion powers the sun, and why we remain anchored to this planet. It stands as the most rigorously tested, most triumphant framework in the entire chronicle of human thought. It assures us that the cosmos is homogeneous, orderly, and fundamentally comprehensible. There exists merely one complication. Reality itself refuses to cooperate. When we direct our most powerful instruments toward the heavens, we discover phenomena that categorically contradict our expectations. We observe cosmic structures whose very existence violates our theories. We detect matter in motion, at velocities that defy explanation. We witness energy manifesting from absolute emptiness. It resembles discovering an additional room in a house whose blueprints you drew yourself. That room has no business existing, yet there it stands. And these discrepancies aren't minor computational rounding errors. These are colossal, glaring contradictions screaming at us that our fundamental comprehension of existence might be catastrophically mistaken. We are identifying celestial objects that contradict the established chronology of cosmic creation. We are intercepting transmissions from the supposed emptiness of space. We are measuring supposedly unchanging values that appear to be shifting. So we are going to examine every piece of evidence, holding nothing back. From the inexplicable temperature anomalies in the farthest reaches of observable space to the mysterious absence of predicted matter in our immediate cosmic neighborhood, we are going to explore the 50 distinct ways the universe is violating everything we thought we understood. Because at this moment in history, our scientific certainties are crumbling, and the more precisely we measure, the more bewildering everything becomes. Let's begin with the largest map ever created. When you examine the most ancient photons in existence, the cosmic microwave background radiation, it ought to resemble white noise on an analog television set. Just arbitrary, minuscule variations in temperature distributed uniformly across every direction we can observe. This represents the cosmological principle in action. The universe should exhibit identical properties regardless of which direction you look. No privileged locations, no inexplicable formations. But then our instruments detected the cold spot, initially identified by the Wilkinson Microwave Anisotropy Probe and subsequently verified by the Planck satellite mission. It constitutes an enormous region in the southern celestial hemisphere that simply violates all predictions. It registers significantly colder than every surrounding region, approximately 70 to 150 microkelvin below the expected temperature. That might sound insignificant to the uninitiated, but in cosmological terms, this represents the difference between a gentle wave and a catastrophic tsunami. From a statistical standpoint, it has no right to exist. The probability of a feature this expansive and this anomalous appearing randomly within our theoretical framework is substantially less than 1%. It stands out like a festering wound on an otherwise unblemished surface. So the scientific community did what it always does when confronted with the impossible. They searched exhaustively for experimental error. They recalibrated the measurement instruments. They accounted for potential interference from interstellar dust. They investigated every conceivable source of contamination. But the anomaly persisted. It is genuine, and it is massive. So if the cold spot doesn't represent measurement error, what precisely is it? The most palatable explanation invokes a void. More specifically, a supervoid. Picture an incomprehensibly vast region of space, roughly 1.8 billion light-years in diameter, positioned in the constellation Eridanus, an area containing dramatically fewer galaxies, stellar formations, and gas clouds than cosmic averages would predict. Just boundless, desolate space. The theoretical mechanism is straightforward. As photons from the cosmic microwave background traverse space on their journey toward our detectors, they must pass through this enormous emptiness. Because gravitational potential is substantially reduced in this region, the photons lose energy as they effectively climb out of this gravitational well on the far side. This phenomenon is termed the integrated Sachs-Wolf effect. Reduced photon energy manifests as decreased temperature. Mystery solved, correct? Not remotely. We did indeed identify a void in that specific direction. The Eridanus supervoid. It represents the largest known void in the observable universe. But here lies the critical problem. It isn't sufficiently empty. Even a void of such staggering proportions can only account for approximately 10 to 20% of the observed temperature deficit we measure in the cold spot. The mathematics, categorically, does not reconcile. The void definitely exists, but attempting to explain the cold spot with this void alone is equivalent to attributing a completely shattered window to a tiny pebble. The magnitude of the effect vastly exceeds what the proposed cause could produce. Therefore, the fundamental question persists. What mechanism generated the remaining temperature anomaly? This brings us to the hypothesis that makes credentialed scientists profoundly uncomfortable because it sounds indistinguishable from speculative fiction. What if the cold spot didn't originate in our universe at all? Certain theoretical physicists, including Laura Mersini-Houghton, have proposed that our universe might not represent the sole bubble of spacetime floating in the quantum foam. We could constitute merely one component of a multiverse. And during the earliest moments of our cosmic history, throughout the violent inflationary expansion following the Big Bang, our bubble of spacetime might have collided with an adjacent one, a neighboring universe. If two discrete universes experienced a collision, the impact would necessarily leave evidence, a cosmological scar. It would redistribute matter asymmetrically and leave behind a region exhibiting distinctive properties, a cold spot. Now, to be absolutely transparent, this does not represent mainstream scientific consensus. It constitutes a radical proposition. But the mere fact that we must seriously entertain such possibilities tells you everything about how profoundly strange this observation is. We are observing a section of the sky that adamantly refuses to conform to our theoretical framework, compelling us to question whether, perhaps, just perhaps, our reality possesses boundaries, and something collided against them from beyond. If the possibility of damage from another universe doesn't sufficiently unsettle you, let's discuss the axis of evil. And no, that isn't hyperbolic language. That represents the actual terminology cosmologists employ. Remember the fundamental premise that the universe should be statistically random? That no directional preference should exist in space? Well, when researchers analyzed the temperature fluctuations in the cosmic microwave background with unprecedented precision, they discovered a pattern, an unmistakable alignment. The regions of elevated and reduced temperature aren't scattered randomly throughout space. They appear to align along a specific axis. And the most disturbing aspect of this discovery is that this axis aligns almost perfectly with the plane of our own solar system. Consider how absolutely insane that is. We are examining background radiation that originated 13 billion years ago. It has absolutely no causal relationship with Earth. It has no connection to our sun. It shouldn't exhibit any correlation whatsoever with the orbital configuration of our planets. And yet, the empirical data suggests the entire universe possesses an orientation centered around our location. Copernicus devoted his entire existence to proving we don't occupy a privileged position in the universe. The axis of evil seems to be suggesting that perhaps we are cosmologically special after all. Or far more likely, something is systematically flawed in our understanding of cosmic structure. Perhaps some exotic topology, like a universe possessing the shape of a torus that naturally produces these alignments. Regardless, the cosmic map isn't random. It possesses a preferred direction, and we have no explanation why. While we are examining maps that contradict our theories, let's discuss cosmic traffic patterns. In an expanding universe governed by standard cosmology, everything should be receding from everything else. It resembles dots marked on the surface of an inflating balloon. If you observe distant enough regions, the expansion should constitute the only significant motion. But in 2008, a research team led by Alexander Kashlinsky discovered something entirely different. They analyzed the velocities of hundreds of galaxy clusters and found that they weren't simply participating in cosmic expansion. They were drifting. An enormous river of galaxies extending across billions of light years is flowing in a common direction at nearly 2 million miles per hour. They designated it dark flow. It is occurring independently of the cosmic expansion. It resembles throwing numerous corks into an exploding lake and observing them all drift sideways against the primary current. The drift is directed toward a specific patch of sky between the constellations Centaurus and Hydra, and whatever gravitational influence is pulling them must be absolutely enormous, substantially more massive than anything we can observe within the observable universe. But we cannot detect it. The flow just proceeds in that direction. Part of this motion is attributable to a local gravitational monster we call the Great Attractor. This represents a gravitational anomaly situated approximately 250 million light-years from our position, located directly in what astronomers call the zone of avoidance. That represents the section of sky obscured by the dense dust clouds of our own Milky Way galaxy. We cannot observe it directly using optical telescopes. It is concealed behind a cosmic curtain, but we can measure its gravitational influence. Entire galaxy clusters, including our own, are being pulled toward it at hundreds of kilometers per second. The Great Attractor itself is now understood to be merely a component of something even larger and more incomprehensible, the Laniakea supercluster. This represents a gravitationally bound structure containing 100,000 galaxies spanning 520 million light-years. Our entire local group of galaxies constitutes merely a tiny suburb in this cosmic metropolis. But even Laniakea doesn't explain dark flow. The motion extends far beyond what local gravitational attraction could produce. The galaxies are flowing towards something outside our observable universe. Think about the implications. There exists something so massive, so gravitationally dominant, that it can pull galaxy clusters across cosmic distances we cannot even observe. It is beyond our cosmic horizon. Some astronomers propose it might be the gravitational influence of matter that existed before inflation, structures from a previous epoch that got stretched beyond visibility. Others suggest it could be evidence of mass concentrations in adjacent universe bubbles in an eternal inflation scenario. The most unsettling possibility is that we are detecting the gravitational signature of another universe entirely, one that exists parallel to ours, pulling on our matter through higher dimensional space. Regardless of the explanation, dark flow tells us that the cosmic expansion isn't the only game in town. There are deeper currents, invisible tides pulling the universe in directions we cannot predict or explain. We thought we understood cosmic motion. We were wrong. Now let's talk about something that shouldn't exist at all, but does anyway. The largest structures in the universe. According to the cosmological principle, matter should be distributed relatively uniformly across sufficiently large scales. There should be a maximum size to cosmic structures, because gravity only had a finite amount of time to pull matter together since the Big Bang. That maximum size is called the cosmological horizon, roughly 1.2 billion light-years across. Nothing larger should exist, because there simply hasn't been enough time for gravity to assemble it. In 1991, astronomers discovered the Claus-Campusano Large Quasar Group, 2 billion light-years long. That already exceeded theoretical limits. Then we found the Sloan Great Wall, 1.3 billion light-years across, still within the realm of barely acceptable. Then in 2013, we discovered the Hercules Corona Borealis Great Wall, 10 billion light-years across. 10 billion. That is approximately 10% of the diameter of the observable universe. This structure is so incomprehensibly massive that light would require 10 billion years just to traverse it. To put that in perspective, that structure is larger than the time elapsed since the Big Bang would theoretically allow. It shouldn't exist. Not according to our timeline, not according to our gravitational models, not according to anything in the standard cosmological framework. The existence of the Hercules Corona Borealis Great Wall violates the fundamental assumption that the universe is homogeneous at large scales. It suggests that either our cosmological principle is wrong, or the timeline of structure formation is wrong, or both. And it gets worse. We keep finding more of these impossible structures. The giant arc discovered in 2021 spans 3.3 billion light-years. The Big Ring discovered in 2024 measures 1.3 billion light-years in diameter. These aren't just at the edge of acceptability. They're deep into the realm of the impossible. And astronomers are finding them regularly now. It is like the universe is deliberately constructing things that contradict our theories. Some cosmologists have tried to explain these structures as statistical flukes, arguing that if you look at enough of the sky, you'll eventually find apparent patterns that don't actually mean anything. But the mathematics doesn't support this dismissal. The probability of these structures arising by chance in our standard cosmological model is astronomically small. We are talking about 1 in a million odds, and we've found multiple examples. Others have proposed that these structures aren't actually gravitationally bound, that they're just chance alignments of smaller structures that happen to appear connected from our perspective. But spectroscopic analysis confirms these are genuine physical structures, not optical illusions. The quasars and galaxies within them share common velocities and distances. They're real. The most radical explanation is that our understanding of cosmic time is fundamentally flawed. If the universe is older than we think, or if structure formation occurred faster than our models predict, then these massive structures become possible. But that would require revising nearly everything we think we know about cosmic history. It would mean the Big Bang timeline needs major corrections. We are staring at structures that are telling us point blank that something is deeply wrong with our cosmic narrative. Either the universe had more time than we thought, or gravity works differently at cosmic scales, or there were initial conditions we don't understand that seeded these massive formations. Regardless, the largest structures in the universe are impossible according to our best theories, and they're sitting right there in the sky, defying us to explain them. While we are discussing things that break our timeline, let's examine something even more immediate and disturbing: stars that are older than the universe itself. This isn't theoretical speculation. These are measured ages from stellar astrophysics. The universe, according to our most precise measurements of the cosmic microwave background, is 13.8 billion years old. That number has been refined repeatedly and is considered one of our most reliable cosmological measurements. Now, when astronomers study the oldest stars we can find, particularly metal-poor stars from the earliest generations, they use well-established techniques to determine their ages. They analyze their brightness, temperature, chemical composition, and position on the Hertzsprung-Russell diagram. The physics is solid. We understand stellar evolution quite well. The problem? Some of these ancient stars calculate out to be 14 to 15 billion years old, older than the universe. The most famous example is the star HD 140283, nicknamed Methuselah. For years, its estimated age was 14.5 billion years, give or take 800 million years. Even accounting for measurement uncertainty, the lower end of that range was still older than the universe. Revised calculations have brought it down to around 14.3 billion years, but that still creates an uncomfortable overlap with the age of the universe. The margins of error barely save us from absolute contradiction, and Methuselah isn't alone. Several other extremely metal-poor stars in the galactic halo show similarly problematic ages. These are stars that formed when the universe contained almost no elements heavier than hydrogen and helium, meaning they're from the first or second generation after the Big Bang. So how do we resolve this? Astronomers have been trying desperately. Some argue the stellar age calculations must be wrong, that we're missing something in our understanding of how these ancient stars evolve. Maybe mass loss occurs differently than we think, or maybe nuclear reaction rates in extremely metal-poor environments don't match our laboratory measurements. These are reasonable scientific adjustments, but others look at the cosmic age determination and wonder if that's where the error lies. What if the universe is actually older than 13.8 billion years? What if our interpretation of the cosmic microwave background, or our cosmological parameters like the Hubble constant, are slightly off? If the universe were 14.5 or 15 billion years old, these stellar ages would fit comfortably. But changing the age of the universe isn't a minor adjustment. It would require revising the entire lambda CDM cosmological model. It would affect calculations of dark energy density, matter density, and the timeline of cosmic structure formation. It would ripple through every corner of cosmology. The most unsettling possibility is that both measurements are correct, and something else is wrong. Perhaps stellar evolution in the very early universe proceeded differently than we understand. Perhaps these stars formed from primordial matter that was enriched by some mechanism we haven't considered, making them appear older than they are. Or perhaps most disturbingly, perhaps the timeline of the Big Bang itself isn't linear. If time experienced different rates of passage in the early universe, or if cosmic inflation created temporal anomalies, then comparing stellar ages to cosmic age becomes meaningless. We are measuring objects with chronometers that might not be calibrated to the same clock. For now, the scientific community has settled into an uneasy compromise. They've massaged the numbers just enough that the error bars overlap and everyone can sleep at night. But make no mistake, we are looking at stars that, according to our best physics, are too old to exist. And that means, somewhere in our understanding of cosmic time, there's a crack. Let's move from the impossibly old to the impossibly fast. Black holes that grew too quickly. In 2023, the James Webb Space Telescope began sending back images of the early universe with unprecedented clarity. Astronomers were excited to see what the first galaxies looked like, how they formed, how they evolved. What they found was absolutely shocking. Massive, fully formed galaxies existing just a few 100 million years after the Big Bang. Galaxies that should not exist yet. But it gets worse. At the centers of these impossibly early galaxies, we found supermassive black holes. Not small, stellar mass black holes, but monsters containing millions to billions of solar masses. Sitting there fully formed, when the universe was barely 3% of its current age. According to our models of black hole growth, this is impossible. Black holes form from collapsed stars. They then grow by accreting matter from their surroundings, and occasionally merging with other black holes. This is a slow process. Even under optimal conditions, with unlimited fuel and perfect efficiency, the maximum growth rate is limited by the Eddington limit. This is the point where radiation pressure from infalling matter becomes so intense it blows away any additional material trying to fall in. The Eddington limit means black holes can at most double their mass every few tens of millions of years. Do the math. Starting from a stellar mass black hole of, say, 10 solar masses, and doubling every 50 million years for the first 500 million years of cosmic history, you can reach maybe 10,000 solar masses. Perhaps 100,000 if you push every assumption to the limit. But we are finding black holes with millions and billions of solar masses in galaxies that are only 500 million years old. The numbers don't work. Not even close. To reach those masses in the available time, these black holes would need to be feeding at rates far exceeding the Eddington limit. They would need to be growing impossibly fast. So, how do we explain this? One possibility is that these black holes didn't start small. Maybe they began as intermediate mass black holes, containing thousands or tens of thousands of solar masses right from the start. But how? Standard stellar collapse can't produce black holes that massive. You'd need direct collapse of enormous primordial gas clouds, a process we've theorized, but never confirmed. Another option is that the early universe had feeding conditions so extreme that black holes could exceed the Eddington limit. Maybe in dense primordial environments, radiation couldn't escape efficiently, allowing super Eddington accretion. Maybe early black holes merged constantly in the crowded conditions of the first galaxies. These are plausible adjustments, but they're also admissions that our models of early universe conditions are fundamentally incomplete. The most radical explanation is that these aren't regular black holes at all. Some physicists have proposed that primordial black holes, formed directly from density fluctuations in the first moments after the Big Bang, could serve as seeds. These would be black holes that never went through a stellar phase, black holes that existed before the first stars ever ignited. If primordial black holes are real and sufficiently massive, they could explain the early supermassive black holes we're observing. But here's the problem. We have no direct evidence that primordial black holes exist. They're theoretically possible, but we've never detected one. Invoking them to solve the early black hole problem is essentially inventing an unproven phenomenon to explain an impossible observation. It might be correct, but it's not satisfying. What we're really looking at is another timeline violation. The universe appears to have assembled complex structures, both galaxies and supermassive black holes, far faster than our physics allows. Either the timeline is wrong, the growth mechanisms are wrong, or the initial conditions of the universe were radically different than we assume. The James Webb Space Telescope hasn't solved these mysteries. It has made them dramatically worse. Every new deep field image reveals more impossibly early, impossibly massive structures. The more we look, the more we find objects that shouldn't exist yet. And we're forced to confront the possibility that our entire understanding of how the universe assembled itself might be fundamentally flawed. We've been building models based on assumptions that seemed reasonable, but reality is showing us those assumptions were wrong. Now let's talk about something that exists in abundance, but remains completely invisible: dark matter. This is the ghost that holds the universe together. Astronomers have known something was wrong since the 1930s, when Fritz Zwicky studied the Coma galaxy cluster. He measured how fast galaxies within the cluster were moving and calculated how much mass would be needed to keep them gravitationally bound. The visible matter, all the stars and gas we could see, accounted for less than 1% of the required mass. Either the galaxies should be flying apart, or there was massive amounts of invisible matter holding everything together. He called it missing mass. For decades, astronomers hoped they were just missing visible matter, that there were huge quantities of dim stars or cold gas they hadn't detected. But every improvement in telescopes and detection methods confirmed the deficit. In the 1970s, Vera Rubin studied rotation curves of spiral galaxies. She measured how fast stars orbit at different distances from galactic centers. According to Newtonian gravity, stars farther from the center should orbit slower, just like planets in our solar system. But that's not what she found. Stars at the edges of galaxies were orbiting just as fast as stars near the center. The only explanation was that galaxies are embedded in enormous halos of invisible matter extending far beyond the visible disk. Matter that doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. Matter we can only detect through its gravitational influence. We call it dark matter, and it constitutes approximately 85% of all matter in the universe. Think about that. Everything we can see, every star, every galaxy, every nebula, every planet, every atom in your body, all of it together makes up only 15% of the matter that exists. The rest is invisible, intangible, and completely mysterious. We know dark matter is there because we can see its effects everywhere. Galaxy rotation curves only make sense if dark matter exists. Gravitational lensing, where massive objects bend light from background sources, reveals dark matter distributions. The cosmic microwave background patterns require dark matter to form the structures we see today. Computer simulations of galaxy formation only work if you include dark matter. Remove it, and everything falls apart. So, we know it exists. We know approximately how much exists. We know roughly where it exists. But we have absolutely no idea what it is. For decades, the leading hypothesis was WIMPs, weakly interacting massive particles. These would be heavy, subatomic particles that barely interact with normal matter, passing through it like ghosts. Physicists built enormous underground detectors, shielded from cosmic rays, hoping to catch rare interactions between dark matter particles and normal atoms. They've been searching for decades. They've found nothing, not a single confirmed detection. The sensitivity of these experiments has improved by orders of magnitude. They should have detected WIMPs by now if they exist in the quantities needed to explain dark matter. But the detectors remain silent. This has led to alternative theories. Maybe dark matter is made of axions, hypothetical ultralight particles that barely interact with anything. Maybe it's primordial black holes scattered throughout the universe. Maybe it's something even more exotic, particles from a completely separate dark sector that only interacts with our matter through gravity. Or maybe, just maybe, dark matter doesn't exist at all. Maybe gravity itself works differently than we think. This is called modified Newtonian dynamics, or MOND. The idea is that at very low accelerations, like those found at the edges of galaxies, gravity's strength doesn't follow the inverse square law anymore. It behaves differently in ways that could explain rotation curves without needing invisible matter. MOND has had some successes. It can explain galaxy rotation curves quite well, but it fails catastrophically when applied to galaxy clusters and the cosmic microwave background. It also can't explain gravitational lensing observations, where we see mass-bending light from locations where no visible matter exists at all. The universe seems to demand that dark matter is real, not just a modification of gravity. So we're left in an absurd situation. We know that 85% of the matter in the universe exists. We can map where it is. We can measure its gravitational effects. But we cannot detect it directly. We don't know what it's made of. And every experiment designed to find it has failed. We are living in a universe dominated by invisible substance that we cannot see, cannot touch, cannot capture, and cannot identify. It's like being told that your house is filled with invisible people who move your furniture around when you're not looking. You can see the furniture moving, you can measure the weight distribution, but you can never see or interact with whoever is doing it. That's our relationship with dark matter. And if that wasn't unsettling enough, dark matter isn't even the strangest invisible component of the universe. That distinction belongs to dark energy. Dark energy represents something even more incomprehensible than dark matter. At least with dark matter, we understand what it does. It clumps together. It holds galaxies together. It behaves like matter should behave, just invisible matter. Dark energy does something that violates every intuition we have about how the universe should work. It pushes everything apart. It makes the universe expand faster. In 1998, two independent research teams studying distant supernovae made a discovery that would earn them the Nobel Prize and shatter cosmology. They were measuring Type Ia supernovae, which serve as standard candles, because they always explode with the same brightness. By comparing how bright they appear to how bright they should be, you can calculate their distance. By measuring their redshift, you can determine how fast they're moving away from us. The teams expected to measure the rate at which cosmic expansion was slowing down. Everyone knew the universe was expanding since the Big Bang, but everyone also assumed that gravity would gradually slow that expansion over time. Matter attracts matter. The universe should be decelerating. Instead, they found the opposite. Distant supernovae were dimmer than expected, meaning they were farther away than they should be. The universe wasn't decelerating, it was accelerating. The expansion of space itself was getting faster. This made absolutely no sense. There's nothing in general relativity, nothing in our understanding of gravity and matter that would cause expansion to accelerate. It would be like throwing a ball in the air and watching it speed up as it rises instead of slowing down. It violates basic physics. But the data was clear. Multiple independent measurements confirmed it. The universe is expanding faster now than it was billions of years ago, and the acceleration is increasing. To explain this, cosmologists were forced to introduce something completely new into their equations. They called it dark energy. They don't know what it is. They don't know where it comes from. They just know it must exist because otherwise the observations make no sense. Dark energy appears to be a property of space itself. The more space exists, the more dark energy exists, and the stronger the repulsive effect becomes. As the universe expands and creates more space, dark energy becomes more dominant, accelerating expansion even faster. It's a runaway process, and it constitutes roughly 68% of all the energy in the universe. Let that sink in. 68% dark energy, 27% dark matter, 5% normal matter, everything we can see and touch. 95% of the universe is invisible and mysterious. We only understand 5% of reality. The most common explanation for dark energy is that it represents vacuum energy, the baseline energy of empty space itself. Quantum field theory predicts that even completely empty vacuum isn't truly empty. Virtual particles constantly pop in and out of existence. Quantum fields fluctuate. This should create a small but non-zero energy density, even in perfect vacuum. The problem is, when physicists calculate what the vacuum energy should be based on quantum mechanics, they get an answer. And when they measure what dark energy actually is based on cosmic expansion, they get a different answer. How different? The calculated value and the observed value differ by a factor of 10 to the power of 120. That's 1 followed by 120 zeros. This is called the cosmological constant problem, and it represents the worst prediction in the history of physics. We're not off by a little bit. We're off by more than a Google. Our theoretical prediction is so catastrophically wrong that it's not even in the same universe as the measured value. Some physicists argue that there must be some unknown mechanism that cancels out most of the vacuum energy, leaving only the tiny amount we observe as dark energy. But nobody has the slightest idea what that mechanism would be, or why the cancellation would be so precise. It would require fine-tuning to 120 decimal places. Others suggest that our entire approach to calculating vacuum energy is fundamentally flawed, that we're missing some basic principle of quantum field theory, but nobody knows what that principle would be. The cosmological constant problem remains completely unsolved. We have no idea why the vacuum energy is so much smaller than it should be. We just know that if it were anywhere close to the predicted value, the universe would have exploded apart instantly after the Big Bang and no structures would exist. We're here because of a discrepancy we cannot explain. There's another possibility that's even more disturbing. Maybe dark energy isn't constant. Most cosmological models treat dark energy as a cosmological constant, a fixed property of space that never changes. But what if it's dynamic? What if dark energy's strength varies over time or across space? Some observations hint at this. Measurements of cosmic expansion at different epochs seem to show slight variations in dark energy density. These variations are small and could be measurement errors. But if they're real, it means dark energy is something more complex than vacuum energy. It would be a dynamic field, something that evolves and changes. Physicists call this quintessence, and it would completely change our understanding of the universe's future. If dark energy is increasing in strength, the acceleration of expansion will become more extreme. Eventually, billions of years from now, expansion could become so rapid that it tears apart gravitationally bound structures. First, galaxy clusters would be pulled apart. Then, galaxies themselves. Then solar systems. Then planets. Then molecules. Then atoms. Then atomic nuclei. This is called the Big Rip, and it represents one possible fate of the universe if dark energy continues to strengthen. Everything gets torn apart down to the subatomic level. Alternatively, if dark energy is decreasing or unstable, it could suddenly vanish or even reverse sign. If it reversed, it would switch from pushing space apart to pulling it together, causing the universe to collapse in a big crunch. We have no way to predict which scenario is correct because we don't understand what dark energy is or how it behaves. We're flying blind into the future. The existence of dark energy also raises a profound question about why we exist now. If dark energy has always been present, there was a long period in cosmic history when matter dominated and dark energy was insignificant. During that era, gravity could pull matter together to form galaxies and stars and planets, and eventually, life. But that era is ending. Dark energy is becoming dominant. In the far future, dark energy will prevent any new structures from forming. The universe will become increasingly empty and cold as galaxies accelerate away from each other beyond the cosmic horizon. Stars will burn out, black holes will evaporate, and nothing new will form. We happen to exist during the brief cosmic epoch, when structure formation is possible. Before this epoch, the universe was too hot and dense. After this epoch, it will be too diffuse and dominated by dark energy. Why are we here now? Is it just coincidence? Or is there some anthropic principle at work where observers can only exist during the narrow window when conditions permit complexity? This is uncomfortable because it suggests our existence is tied to a cosmic accident of timing. We're not just on a small planet orbiting an average star. We're living during a temporary moment in cosmic history. The universe's past was chaos and fire. Its future will be emptiness and cold. We exist in the brief intermission between those states, and we have no idea why. Dark energy also creates an observational horizon problem. Because distant galaxies are accelerating away from us faster and faster, there will come a point where they're receding faster than light can travel through expanding space. Once that happens, we will never be able to see them again. They cross beyond our cosmic horizon. This is already happening. There are galaxies we can see now that are accelerating away so rapidly that any light they emit from this point forward will never reach us. We're watching them freeze at a particular moment in time, and then fade from view as their earlier light finally reaches us, and then nothing more ever arrives. In 1 trillion years, If any civilizations still exist, they will look at the sky and see almost nothing. Their observable universe will contain only their local gravitational group of galaxies, everything else having accelerated beyond visibility. They will have no way to discover the Big Bang, no cosmic microwave background to measure, no distant galaxies to study. They will look at an empty universe and have no evidence that it was ever different. They won't be able to discover cosmology. Their cosmology will be wrong. We are incredibly fortunate to exist during the era when we can still observe the cosmos beyond our local neighborhood, when we can still detect the cosmic microwave background, when we can still measure expansion, but that window is closing. Dark energy is erasing the evidence of cosmic history. Future observers will inherit a universe scrubbed clean of information. They will live in ignorance, not because they're less intelligent, but because the universe has destroyed the clues. This makes you wonder, what information has already been destroyed? What evidence of cosmic history existed in the early universe that no longer exists? What phenomena occurred in the first moments after the Big Bang that left no trace we can currently detect? If the universe is erasing its own history, how much has already been lost? How much are we already missing? Let's shift from invisible components to visible impossibilities. The cosmic web should not look like it does. When cosmologists run simulations of structure formation, starting from the smooth conditions of the early universe and allowing gravity to pull matter together over billions of years, they get a specific pattern. Matter collects along filaments, creating a vast cosmic web of galaxies connected by bridges of gas and dark matter, with enormous voids in between. And when we observe the actual universe, we do see a cosmic web. It matches the simulations beautifully. Too beautifully. The problem is the scale. The simulations predict that the cosmic web should have a characteristic scale, a typical size for the filaments and voids based on the density fluctuations in the early universe and the amount of time gravity has had to work. That scale is around 300 million light years. Filaments and voids should cluster around that size, with some smaller and some larger, following a statistical distribution. But when astronomers map the actual cosmic web in detail, they find filaments and voids that are far larger than predicted. We're finding voids exceeding 1 billion light years across. We're finding filaments extending billions of light years. These structures are too large to have formed in the time available since the Big Bang. Gravity simply hasn't had enough time to create structures that massive, even with dark matter helping. This is the same problem we saw with the Hercules Corona Borealis Great Wall, but it's not limited to one structure. It's systemic. The entire cosmic web appears to be scaled up beyond what our models predict. Either the initial density fluctuations were much larger than we think, or structure formation occurred much faster than we understand, or there's some additional force or mechanism we haven't accounted for. Some cosmologists have proposed that cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, could serve as seeds for structure formation. These cosmic strings would create gravitational wells along their length, attracting matter and forming filaments faster than normal gravity alone could achieve. But we have no direct evidence cosmic strings exist. Again, we're inventing theoretical objects to explain impossible observations. Others suggest that dark matter might not be uniformly distributed in the early universe. If dark matter had its own structures or fluctuations independent of normal matter, it could create larger initial seeds for structure formation. This is called dark matter isocurvature perturbations. But measurements of the cosmic microwave background strongly constrain how much isocurvature could have existed. There's not enough room in the data to explain the structures we see. The most disturbing possibility is that the universe is not homogeneous at the scales we assumed. The cosmological principle states that the universe looks the same in all directions when averaged over sufficiently large scales. We thought that scale was a few hundred million light years. But if structures exist at billion light-year scales and larger, then maybe the universe is only homogeneous at scales larger than our observable universe. If that's true, then we're seeing a biased sample. We're looking at one small patch of a much larger cosmos that might have wild variations beyond what we can observe. Our observable universe might be an unusual region, slightly denser, or with unusual initial conditions that allowed these massive structures to form. But we'd have no way to know, because we can't see beyond our cosmic horizon This creates a testability problem. If the explanation for cosmic web anomalies lies beyond what we can observe, then we can never verify it. We're left with observations that contradict our models and no way to resolve the contradiction because the answer exists outside our observable domain. Science requires testable predictions. If the cosmos is hiding answers beyond observation, we're stuck. Now let's discuss something even more immediate and puzzling. The planets in our own solar system don't orbit exactly as they should. This has been known for over a century. When astronomers calculated planetary orbits using Newtonian gravity and later general relativity, they found small discrepancies. Mercury's orbit precessed slightly more than Newton predicted. Einstein's general relativity explained that precession perfectly, confirming relativity and solving the mystery. But other discrepancies remained. The outer planets, particularly Neptune and Uranus, showed tiny orbital anomalies that couldn't be explained by known forces. For decades, astronomers assumed these discrepancies were due to measurement errors, or small unknown asteroids and comets perturbing the orbits. But as measurements became more precise, the anomalies persisted. In the 1980s, astronomers noticed something strange. The Pioneer spacecraft, Pioneer 10 and 11, launched in the 1970s to explore the outer solar system, were slowing down. Not dramatically, but measurably. They were experiencing a tiny constant acceleration toward the sun that couldn't be explained by gravity, solar radiation pressure, or any known force. The deceleration was incredibly small, about 8.7 times 10 to the minus 10 meters per second squared. That's almost nothing. But it was consistent and measurable. This became known as the Pioneer anomaly. For years, it was a genuine mystery. Some physicists speculated it might be evidence of modified gravity at solar system scales, or drag from dark matter, or some unknown force. Eventually, detailed thermal modeling showed the anomaly could be explained by anisotropic heat radiation from the spacecraft themselves. The plutonium power sources emitted heat preferentially in certain directions, creating a tiny rocket effect. Mystery solved, probably. But then the Voyager spacecraft started showing similar but not identical anomalies, and orbital tracking of the outer planets continued to show small, unexplained variations. New Horizons, the spacecraft that flew past Pluto, also experienced trajectory anomalies during its journey. These might all be explainable by complex interactions of thermal effects, gas leaks, and gravitational perturbations. But the sheer number of small anomalies in the outer solar system is unsettling. There's also the Moon's orbit. The Moon is receding from Earth at about 3.8 centimeters per year due to tidal interactions. This is well understood and precisely measured using laser ranging to reflectors left on the lunar surface by Apollo astronauts. But when you calculate the tidal energy transfer required to produce that recession rate and compare it to the energy dissipation measured in Earth's oceans, there's a mismatch. The Moon is receding faster than tidal friction in the oceans can explain. Additional energy dissipation must be occurring somewhere, possibly in solid body tides in Earth's mantle, or in the ocean floor, or perhaps our models of tidal mechanics are incomplete. It's a small discrepancy, but it's there. Then there's the Kuiper Belt. This region beyond Neptune contains millions of icy bodies, remnants from the solar system's formation. The Kuiper Belt should extend smoothly outward until gravitational perturbations from Neptune and other planets create gaps and resonances. And it does, up to a point. But at about 50 astronomical units from the Sun, the Kuiper Belt suddenly ends. There's a sharp edge. Beyond that edge, almost nothing exists until you get to the scattered disk and Oort cloud at much greater distances. This is called the Kuiper Cliff. Why does it exist? If the solar system formed from a smooth disk of material, the Kuiper Belt should fade gradually, not cut off sharply. Some astronomers propose that an undiscovered planet, Planet 9, exists in the outer solar system, and its gravity cleared out the region beyond the Kuiper Cliff. This hypothetical planet would be several times Earth's mass, orbiting hundreds of astronomical units from the Sun. Multiple lines of evidence suggest Planet 9 might exist. Several distant Kuiper Belt objects have orbits that cluster in unusual ways, suggesting they're being gravitationally shepherded by an unseen massive object. Orbital simulations show that a planet in the right location could explain these clustered orbits and the Kuiper Cliff. But despite extensive searches, nobody has found Planet 9. It remains hypothetical. If it exists, it's extremely distant and extremely dim, making detection incredibly difficult. But the alternative is that the clustered orbits and the Kuiper cliff are coincidences, which seems unlikely. So we might have an entire planet in our own solar system that we haven't discovered yet. Or there might be some other dynamical process we don't understand that created the Kuiper cliff in orbital clustering without requiring an additional planet. Either option is unsettling. Either we're missing a major component of our own solar system, or our understanding of solar system dynamics is incomplete. Both possibilities suggest we don't fully understand even our local cosmic neighborhood. And then there's the matter of solar system formation itself. The NICE model, named after the French city where it was developed, proposes that the outer planets didn't form in their current positions. Jupiter, Saturn, Uranus, and Neptune started in different orbits and then migrated inward and outward due to gravitational interactions with the disk of planetesimals left over from solar system formation. This migration explains many features of the solar system, including the distribution of asteroids, the existence of the Kuiper belt, and the late heavy bombardment period, when the inner solar system was pummeled by impacts. But the NICE model has problems. It requires very specific initial conditions to work. The planets need to start in particular orbits, with particular masses and particular resonances. If you change the initial conditions slightly, the model breaks and the planets don't end up where we observe them. This fine-tuning problem suggests either we're incredibly lucky, or the NICE model is incomplete, or there's some additional factor that naturally produces the required initial conditions. Nobody knows which. The formation of Earth itself presents puzzles. Earth is unusually large for a rocky planet in the inner solar system. Venus is similar in size, but Mercury and Mars are much smaller. Why? Standard models of planet formation suggest rocky planets should be relatively similar in size if they form from the same protoplanetary disk. The giant impact hypothesis, where Earth collided with a Mars-sized body early in its history, explains the Moon's formation and some of Earth's properties. But it requires that collision to occur at just the right angle, with just the right speed, to produce the Earth-Moon system we observe. Again, fine-tuning. The presence of water on Earth is also puzzling. Earth formed in the inner solar system, where temperatures were high enough to evaporate water. So, where did Earth's oceans come from? The standard explanation is that comets and asteroids from the outer solar system delivered water after Earth cooled. But isotopic analysis of Earth's water doesn't match comets perfectly. The ratio of deuterium to hydrogen in comet water is typically higher than in Earth's oceans. Some asteroids match better, but then you need to explain how enough water-rich asteroids hit Earth to fill the oceans. It probably happened, but the details remain unclear. Even our sun is weird. The sun's magnetic field reverses polarity every 11 years during the solar cycle. We can observe this happening and measure the effects, but we don't have a complete theoretical understanding of why the cycle is 11 years, or what drives the exact dynamics of the reversal. Solar models can reproduce many features of the solar cycle, but they require tuning parameters to match observations. We don't have a fundamental theory of solar magnetism that predicts the cycle from first principles. The sun also rotates differentially, with the equator rotating faster than the poles. This differential rotation creates the twisted magnetic field lines that produce sunspots and solar flares. But the mechanism that maintains differential rotation against the smoothing effects of viscosity isn't fully understood. There's something about the sun's interior dynamics we're missing. The solar neutrino problem, which puzzled physicists for decades, has been solved. The sun produces neutrinos in its core through nuclear fusion, and we detect them on Earth. For years, we detected only about 1/3 as many neutrinos as solar models predicted. This was a major crisis. Either the sun worked differently than we thought, or neutrinos were doing something unexpected. It turned out to be the latter. Neutrinos oscillate between different types as they travel, and our detectors were only sensitive to one type. When we built detectors that could catch all neutrino types, the total count matched predictions perfectly. Problem solved. But the fact that it took decades to solve tells you how hard it is to be certain about even the closest star. We are living in a solar system that formed through processes we don't fully understand, orbiting a star whose magnetic behavior we can't predict from first principles, on a planet whose water origin remains debated. And there might be an undiscovered planet lurking in the outer darkness. Even home is mysterious. Let's zoom back out to cosmic scales and talk about something truly disturbing. The universe might be rotating. According to the cosmological principle, the universe should have no preferred orientation or rotation. Space should be isotropic. Rotation would imply angular momentum, which would require some initial torque or asymmetry. The Big Bang shouldn't have produced large-scale rotation. But in 2020, analysis of galaxy spins across billions of light years found something unexpected. Galaxies aren't spinning randomly. There's a slight but statistically significant preference for galaxies in certain regions to spin in aligned directions. It's not a strong effect, and it's not universal, but it's there. If confirmed, this would indicate the universe has large-scale structure in angular momentum, a cosmic spin axis. How could this arise? One possibility is that the universe is actually rotating as a whole, but the rotation is so slow we haven't detected it directly. If the universe has even a tiny angular momentum left over from quantum fluctuations in the early universe, it could produce aligned galaxy spins. Another possibility is that tidal torques from the cosmic web structure impart preferred spin directions to galaxies as they form. As matter collapses along filaments, the geometry of the collapse could favor certain spin orientations. This is a known effect at smaller scales, but whether it can produce the observed alignments at cosmic scales is debated. The most exotic explanation is that the universe isn't simply connected. If space has a complex topology, like a three-dimensional donut or Mobius strip, it could create apparent rotations or alignments that aren't actually physical rotations, but rather geometrical effects of how space connects to itself. This would be almost impossible to test directly, but it remains a theoretical possibility. If the universe is rotating, it would have profound implications. It would mean the cosmological principle is violated. The universe would have a special axis, and depending on the rotation rate, it could affect structure formation, the cosmic microwave background, and even the ultimate fate of the universe. A rotating universe could avoid certain types of collapse scenarios and might have different long-term dynamics than a non-rotating one. But before we panic about cosmic rotation, it's important to note that these galaxy spin alignments are controversial. Other analyses of different galaxy catalogs don't always find the same effects. It could be a statistical fluke, or selection bias, or systematic errors in how galaxy spins are measured. More data is needed, but the possibility that the universe rotates is no longer absurd. It's a hypothesis that needs to be tested. Now let's talk about light itself. Light is supposed to be constant. The speed of light in vacuum is exactly 299,792,458 meters per second. It's a defined constant, the foundation of relativity. But what if it wasn't always constant? What if the speed of light was different in the early universe? This is called variable speed of light cosmology, and it's been proposed as an alternative to cosmic inflation. Inflation solves several problems in cosmology, including the horizon problem and the flatness problem, by proposing that the universe underwent exponential expansion in the first fraction of a second after the Big Bang. But inflation requires inventing a new field, the inflaton, and carefully tuning its properties. Some physicists have asked whether you could solve the same problems by allowing the speed of light to be much faster in the early universe. If light traveled faster then, distant regions of the universe could have been in causal contact, even without inflation, solving the horizon problem. If the speed of light then decreased to its current value, it could affect the geometry of space in ways that solve the flatness problem. Variable speed of light cosmology is mathematically consistent, but it faces significant challenges. If the speed of light changed, it would affect other fundamental constants that depend on it. The fine structure constant, which determines the strength of electromagnetic interactions, depends on the speed of light. If the speed of light changed dramatically, atoms wouldn't work the same way, and chemistry would be different. You'd need to carefully construct a theory where multiple constants change together in just the right way to keep physics working. This requires significant fine-tuning. More fundamentally, changing the speed of light violates Lorentz invariance, a cornerstone of relativity. Special relativity is built on the assumption that the speed of light is the same in all reference frames. If you allow it to vary, you need to replace relativity with something else. Some theories attempt this, but they're complex and lack strong empirical support. So, variable speed of light remains a fringe idea, but it's not completely ruled out. Some observations hint that fundamental constants might not be perfectly constant across all of time and space. Measurements of distant quasars, whose light has traveled billions of years to reach us, sometimes show tiny variations in the fine structure, constant compared to local measurements. The differences are incredibly small, maybe a few parts per million, and could easily be measurement errors or systematic biases. But if real, they would indicate that fundamental constants evolve over cosmic time. The fine structure constant determines how strongly electrons bind to atomic nuclei, which affects the wavelengths of spectral lines. By analyzing absorption lines in quasar spectra, where light from the quasar passes through intervening gas clouds, astronomers can measure the fine structure constant at different cosmic epochs. Some studies claim to find a spatial variation where the constant has slightly different values in different directions across the sky. This would be absolutely revolutionary. It would suggest the universe isn't isotropic at the level of fundamental physics. The laws of nature would be different in different places. Other studies find no variation at all, concluding the constant is stable to extraordinary precision. The debate continues, with measurements at the edge of detectability and systematic errors difficult to rule out. But the mere possibility that constants might vary is unsettling. We call them constants because we assume they're constant. If they're not, then the word loses meaning, and we need to explain why they have the values they do and how they change. There's also the question of whether the constants are truly fundamental or emerge from some deeper theory. In string theory, the values of constants like the speed of light, Planck's constant, and the gravitational constant depend on how extra dimensions are compactified. Different compactifications produce different constants. If the universe has regions with different compactifications, you could have domains where physics works differently. This is the landscape problem in string theory. There might be 10 to the 500th possible vacuum states, each with different physical constants. If that's true, then our constants aren't fundamental. They're environmental variables that happen to have certain values in our cosmic neighborhood. This leads to anthropic reasoning. We observe the constants we do because only in universes with these particular values can observers exist. In universes where the electromagnetic force is too strong or too weak, atoms don't form. In universes where gravity is too strong, stars burn out too quickly for life to evolve. We're here because we're in a habitable universe, selected from a vast landscape of possibilities. This is philosophically unsatisfying because it replaces explanation with selection. We're not explaining why the constants have their values. We're just saying we couldn't exist if they were different. It's technically correct, but doesn't feel like understanding. It trades one mystery for another. Let's move to something we can actually see but wish we couldn't. Rogue planets. Standard planet formation occurs in protoplanetary disks around young stars. Planets coalesce from dust and gas, and they remain gravitationally bound to their host stars. But simulations of planetary system formation show that gravitational interactions between forming planets can eject some of them from the system entirely. A close encounter between two planets can send one flying out into interstellar space at high velocity, never to return. These ejected planets become rogues, wandering the galaxy without a sun. For years, this was purely theoretical. But then we started finding them. Microlensing surveys, which detect planets by the gravitational lensing effect they produce when passing in front of background stars, have discovered numerous free-floating planetary mass objects. These objects are too small to be stars or brown dwarfs, but they're not orbiting anything. They're alone in the dark, and there might be billions of them. Statistical analysis of microlensing events suggests there could be more rogue planets in the galaxy than stars. Think about that. For every star you see in the night sky, there might be multiple planets drifting invisibly in the darkness between stars. Most of these rogue planets are likely gas giants, Jupiter mass objects that got ejected during the chaotic early phases of planetary system formation. But smaller rocky planets could also be ejected. Earth-mass rogue planets might exist, frozen worlds with no sun to warm them, drifting eternally through interstellar space. If such a planet retained a thick atmosphere and internal heat from radioactive decay, it could theoretically have liquid water beneath ice sheets and possibly even life. Subsurface oceans, heated by tidal forces or radioactive decay, could provide habitable environments completely independent of stellar radiation. Life on rogue planets would never see stars. It would exist in permanent darkness, sustained by geothermal energy. If technological civilizations could arise on rogue planets, they would have a completely different understanding of the universe. They wouldn't know about stars or galaxies. Their cosmology would be darkness and ice. Only if they developed extremely sensitive infrared astronomy could they discover that the universe contains other objects. The existence of rogue planets also complicates the search for life. We've been focusing on planets in habitable zones around stars. But if habitable rogue planets exist, life could be anywhere. The galaxy could be full of living worlds that we'll never detect because they emit no light and are invisible except during rare microlensing events. We could pass within light years of inhabited rogue planets and never know. There's also a tiny, terrifying possibility that a rogue planet could pass through our solar system. The gravitational perturbation could destabilize planetary orbits or send comets from the Oort cloud into the inner solar system. The odds of a close encounter are incredibly small because space is vast and rogue planets are rare on solar system scales, but it's not zero. We wouldn't see it coming unless it passed close enough to occult background stars or perturb known objects. A rogue planet approaching from certain angles could remain undetected until it was practically on top of us. This is the stuff of disaster movies, but it's not completely impossible. Astronomers are constantly scanning for near-Earth asteroids, but a dark planet-sized object on a hyperbolic trajectory through the outer solar system might not be discovered until too late. The probability is vanishingly small, but the universe has billions of years and countless rogue planets. Unlikely things eventually happen. While we're discussing invisible threats, let's talk about something even more abstract and terrifying: the false vacuum. Quantum field theory tells us that empty space isn't actually empty. It's filled with fields, and these fields can exist in different energy states. The lowest energy state is called the true vacuum. Higher energy states are called false vacuums. If a field is in a false vacuum, it's metastable. It could suddenly decay to the true vacuum, releasing enormous energy in the process. Here's the nightmare scenario. What if the universe is currently in a false vacuum state? What if the Higgs field, which gives particles mass, isn't in its lowest possible energy configuration? If that's true, then at any moment, anywhere in the universe, a quantum fluctuation could cause a tiny region of space to tunnel into the true vacuum. Once that happens, the true vacuum region expands at the speed of light, converting false vacuum to true vacuum and releasing energy. This expanding bubble of true vacuum is called a vacuum decay event. Inside the bubble, the laws of physics are different because the Higgs field has a different value. Particles have different masses. Atoms don't bind the same way. Chemistry doesn't work. Everything is destroyed. And because the bubble expands at light speed, you wouldn't see it coming. There would be no warning. One moment you exist, the next moment the bubble wall hits you and you're disassembled into exotic particles that can't form stable matter. The entire universe could be destroyed this way, one bubble expanding until it consumes everything. And it could start anywhere, at any time, for no reason. This isn't science fiction. This is a genuine possibility, according to quantum field theory. Physicists have calculated the stability of the Higgs vacuum using data from the Large Hadron Collider. The measurements of the Higgs boson mass and the top quark mass determine whether the vacuum is stable, metastable, or unstable. Unfortunately, the measurements put us right in the metastable region. The vacuum is stable against small perturbations, but large quantum fluctuations or high-energy events could trigger decay. The lifetime of a metastable vacuum is probabilistic. It could be 10 to the 100 years, far longer than the current age of the universe, meaning we're safe. Or it could be much shorter. We don't know. The probability depends on details of physics beyond the standard model that we don't understand. Some theories predict the vacuum is perfectly stable. Others predict it's metastable with extremely long lifetimes. A few predict instability could occur much sooner. The most unnerving part is that vacuum decay could have already started somewhere in the universe. If it began 1 billion light years away, the bubble would be expanding toward us at light speed, and we wouldn't know until it arrived. The light carrying information about the bubble can't outrun the bubble itself, so there's no advance warning. You wouldn't see distant galaxies winking out as the bubble consumed them. You'd just be hit without warning. This represents the ultimate existential risk. You can't prepare for it, you can't detect it, you can't prevent it. Either it happens or it doesn't. And if it does, everything ends instantly. Not just humanity, not just Earth, but the entire structure of matter throughout the universe. Some physicists find this possibility oddly comforting. If vacuum decay is possible, and the universe is billions of years old, the fact that it hasn't happened yet suggests the decay rate is incredibly low. We're still here, therefore we're probably safe. This is called the anthropic bound on vacuum decay. But anthropic reasoning has limitations. Just because something hasn't happened yet doesn't mean it won't happen tomorrow. The universe could decay next Tuesday, and there's nothing we could do about it. Let's shift to something less immediately apocalyptic, but equally mysterious. Fast radio bursts. In 2007, astronomers discovered a brilliant pulse of radio waves in archival data from the Parkes telescope. The pulse lasted just a few milliseconds, but released as much energy as the sun emits in an entire day. It came from a distant galaxy billions of light years away. They called it a fast radio burst, or FRB. At first, it seemed like a fluke, maybe a satellite or terrestrial interference. But then they found more, and more. We now know FRBs are common. Thousands occur every day across the entire sky. Most are one-time events, a single brilliant flash from a distant galaxy, never repeating. But some FRBs repeat on irregular schedules, flashing multiple times over months or years from the same location. We have no idea what causes them. The energy requirements are staggering. To produce that much radio emission in milliseconds requires extreme physics. Neutron stars, the collapsed cores of dead massive stars, are the leading suspects. Neutron stars have the strongest magnetic fields in the universe, and sudden changes in these magnetospheres could produce intense radio bursts. Some models invoke magnetars, neutron stars, with magnetic fields thousands of times stronger than normal. Starquakes, or magnetic reconnection events on magnetars, could release bursts of energy matching FRB properties. Other models suggest colliding neutron stars, evaporating primordial black holes, or even white hole eruptions could be responsible. But none of these models explain all the observations. Some FRBs repeat, others don't. Some show complex structure with multiple subpulses. Others are simple single pulses. Some come from active star-forming galaxies. Others from quiet elliptical galaxies. The diversity suggests there might be multiple mechanisms producing FRBs, or the underlying process is more complex than we think. The most scientifically responsible, but least exciting possibility is that FRBs are natural astrophysical phenomena we just haven't figured out yet. But there's another possibility that nobody wants to say out loud. What if some FRBs are artificial? Advanced civilizations with sufficient technology could produce focused radio beams with energies matching FRBs. If you wanted to communicate across intergalactic distances or propel spacecraft using beamed energy, you might create something that looks exactly like an FRB to our telescopes. This doesn't mean FRBs are alien signals. It means we can't definitively rule it out. The Breakthrough Listen project, which searches for signs of extraterrestrial intelligence, monitors FRBs for any patterns or modulations that might indicate artificial origin. So far, nothing conclusive has been found. FRBs appear random and chaotic, lacking the structured patterns you'd expect from intentional communication. But absence of obvious patterns doesn't prove natural origin. A sufficiently advanced civilization might use encoding schemes we can't recognize, or the signals might not be intended for communication at all. They could be leakage from some industrial process or propulsion system. We could be seeing the exhaust from alien starships and interpreting it as astrophysics. This is the problem with detecting alien technology. If you don't know what to look for, you can't distinguish it from natural phenomena. Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic. We could add a corollary. Any sufficiently advanced technology is indistinguishable from astrophysics. FRBs might be natural, they might be artificial, or they might be something we don't have categories for yet. While we're on the topic of aliens, let's discuss the Fermi paradox properly. Enrico Fermi famously asked, "Where is everybody?" The galaxy is billions of years old. It contains hundreds of billions of stars. Even if intelligent life is rare, there should be millions of technological civilizations. Some should be far older than us. Where are they? Why don't we see evidence of their existence? This is the Fermi paradox, and it has no satisfying answer. There are hundreds of proposed solutions, none convincing. Maybe life is incredibly rare. Maybe intelligence is rare. Maybe technological civilizations destroy themselves quickly. Maybe they're here but hiding. Maybe they're not interested in us. Maybe interstellar travel is impossible. Maybe we're looking in the wrong places, or at the wrong wavelengths. Every solution has problems. If civilizations self-destruct, why don't we see ruins or artifacts from billions of years of failed civilizations? If interstellar travel is impossible, why? Physics doesn't forbid it, just makes it difficult. If aliens are hiding, why hide so completely that we see no evidence at all? The most disturbing solution is the dark forest hypothesis. This proposes that the galaxy is full of civilizations, but they're all hiding from each other. The reasoning is game theoretic. If you reveal your location, other civilizations learn about you. You can't know their intentions. If they're hostile and more advanced, they could destroy you. The safest strategy is to remain silent and hidden while listening for others. And if you detect another civilization, you face a terrible choice. If you contact them, you reveal yourself. If they're hostile, you're at risk. The safer option is to destroy them preemptively before they can threaten you. This creates a dark forest where every civilization is an armed hunter moving silently, and any sound, any signal, any fire invites destruction. In this scenario, Earth has been broadcasting radio signals for over a century. We've announced our presence to anyone within 100 light years. If the dark forest hypothesis is correct, we might have already been detected, and our destruction could be in transit, moving toward us at some fraction of light speed. We wouldn't know until it arrived. This is speculation, but it fits the observations. If civilizations follow dark forest logic, we'd see exactly what we observe. Silence. No radio signals. No visible megastructures. No signs of activity. Everyone hiding. And the first civilization to break silence becomes a target. Human SETI projects have not just listened, but transmitted. We've sent deliberate messages to nearby star systems. Some scientists argue this was reckless, that we should remain silent until we understand the risks. Others argue we've already revealed ourselves through a century of radio leakage, so deliberate transmission doesn't change anything. The debate continues, but it highlights how little we know. We're making first contact decisions based on complete ignorance of what's out there. Another solution to the Fermi paradox is the Great Filter. This proposes that there's some step in the evolution from non-life to galaxy-spanning civilization that is extraordinarily difficult. So difficult that almost no one makes it through. The filter could be behind us. Maybe the origin of life is incredibly rare, or the evolution of multicellular life, or intelligence. If so, we're lucky survivors, and the galaxy is mostly lifeless. Or the filter could be ahead of us. Maybe every civilization reaches a certain level of technology and then destroys itself, or gets destroyed by some natural or artificial catastrophe. Nuclear war, bioengineered plagues, nanotechnology run amok, artificial intelligence, vacuum decay triggered by physics experiments. If the Great Filter is ahead of us, our future is grim. We're approaching the barrier that kills everyone. We don't know which scenario is true. We have a sample size of one, but the implications are profound. If we discover microbial life on Mars or Europa, that's bad news. It means the origin of life isn't rare, which means the Great Filter is probably ahead of us. If we find dead civilizations, ruins on distant worlds, that's terrible news. It confirms the filters ahead, and nobody survives. The best possible news would be finding absolutely nothing. Complete sterility everywhere we look would suggest the filter is behind us, we're alone, and we have a future. This is the paradox of the Fermi paradox. Good news feels like bad news. Silence is reassuring. Contact could be catastrophic. We're simultaneously hoping to find aliens and terrified of what it would mean if we do. Let's zoom back to physics fundamentals and discuss something that makes professional physicists uncomfortable. Quantum mechanics and general relativity don't work together. These are our two most successful theories. Quantum mechanics describes the behavior of particles at subatomic scales with extraordinary precision. General relativity describes gravity in spacetime at cosmic scales with extraordinary precision. Both have been tested exhaustively. Both work perfectly within their domains. But when you try to combine them, the math breaks. General relativity treats spacetime as a smooth, continuous fabric. Quantum mechanics says everything is discrete and probabilistic. When you try to quantize gravity, to describe gravitational fields in quantum terms, you get infinities in your equations. The math literally doesn't work. Physicists have developed workarounds. Quantum field theory in curved spacetime treats particles quantum mechanically while treating spacetime classically. This works for most situations but fails at extremes like black hole singularities or the Big Bang, where gravity is strong and quantum effects matter. String theory attempts to resolve this by replacing point particles with tiny vibrating strings. In string theory, gravity emerges naturally as one of the vibrational modes. The theory is mathematically consistent and finite, avoiding the infinities that plague other approaches. But string theory requires extra dimensions, typically 10 or 11 total. These extra dimensions must be compactified, curled up so small we can't detect them. And there are countless ways to compactify them, leading to the landscape problem discussed earlier. String theory also lacks experimental verification. It makes predictions, but they're typically at energy scales far beyond what we can test. We can't build particle accelerators powerful enough to probe string scale physics. So, string theory remains mathematically elegant, but empirically unproven. Loop quantum gravity takes a different approach. It keeps spacetime four-dimensional, but makes it discrete at the smallest scales. Space isn't continuous but grainy, made of tiny loops. This eliminates infinities and makes gravity quantum mechanical. But loop quantum gravity struggles to reproduce general relativity at large scales and doesn't naturally include the other forces. It's a theory of quantum gravity, but not a theory of everything. Other approaches exist: causal set theory, emergent gravity, entropic gravity. None have achieved the success of string theory or loop quantum gravity, and none are complete or tested. The uncomfortable truth is that we don't know how to unify physics. We have two incompatible frameworks that both work perfectly in their respective domains, and we can't reconcile them. This isn't just an academic problem. It means we can't describe black hole interiors. We can't model the first moments of the Big Bang. We can't predict what happens when space-time itself becomes quantum mechanical. We're missing something fundamental. Some physicists believe we need a completely new conceptual framework, something as revolutionary as quantum mechanics was to classical physics. Others think we just need better math and more experimental data. But until we solve quantum gravity, we're stuck. We have blind spots at the most extreme conditions in the universe, and those blind spots hide the deepest secrets. Let's talk about one of those blind spots: black hole information paradox. When something falls into a black hole, what happens to the information it contains? According to general relativity, it crosses the event horizon and falls into the singularity. That information is lost from the universe forever. But quantum mechanics says information can't be destroyed. It can be scrambled and spread out, but the total information content of the universe must remain constant. This is the conservation of information, a fundamental principle of quantum theory. So, we have a contradiction. General relativity says information is destroyed. Quantum mechanics says it can't be. Stephen Hawking made this worse. In the 1970s, by by showing that black holes emit radiation. Hawking radiation arises from quantum effects near the event horizon. Virtual particle pairs pop into existence right at the horizon. Normally they'd annihilate, but if one falls into the black hole and the other escapes, the escaping particle becomes real radiation. The black hole loses mass equal to the energy of the escaping particle. Over immense timescales, black holes evaporate completely. But here's the problem. Hawking radiation is thermal, completely random. It carries no information about what fell into the black hole. So when the black hole evaporates, where did the information go? It can't have been radiated away because Hawking radiation is random. It can't be inside the black hole because the black hole no longer exists. The information seems to have been destroyed, violating quantum mechanics. Physicists have been arguing about this for 50 years. Hawking eventually conceded that information must be preserved somehow. Perhaps it's encoded in subtle correlations in Hawking radiation that we don't know how to calculate. Perhaps it's imprinted on the event horizon in a holographic encoding. Perhaps it escapes through quantum tunneling or wormholes. The holographic principle suggests that all the information about a volume of space can be encoded on its boundary. Applied to black holes, this means everything that falls in is somehow encoded on the event horizon surface. When the black hole evaporates, that information is released in the radiation. This is mathematically elegant but conceptually bizarre. It means reality is holographic, that three-dimensional space is fundamentally a projection of information stored on a two-dimensional surface. If true for black holes, it might be true for the entire universe. We might be living in a holographic projection. Everything you perceive as three-dimensional depth might be information encoded on a distant cosmic boundary. This sounds like simulation theory, and in some sense it is. A holographic universe is computationally equivalent to a simulation. You could describe the entire universe as information processing on a lower dimensional substrate. Whether you call that a hologram or a simulation is semantics. The physics is the same. The black hole information paradox remains unsolved. We don't have a complete theory of quantum gravity to resolve it. Whatever the answer is, it will require radically rethinking the nature of information, space-time, and reality itself. Now let's address something that ties together many of these mysteries: the measurement problem in quantum mechanics. Quantum systems exist in superpositions, multiple states simultaneously, until they're measured. Upon measurement, the superposition collapses into a single definite state. But what constitutes a measurement? What causes collapse? Quantum mechanics describes the evolution of superpositions perfectly, but doesn't explain what happens during measurement. This is the measurement problem, and it's been unsolved since the foundation of quantum theory. The Copenhagen interpretation, the standard textbook version, simply states that measurement causes collapse. It doesn't explain the mechanism. It treats measurement as a fundamental process that's outside the equations. This is philosophically unsatisfying because it divides reality into quantum systems and classical observers, with a mysterious boundary between them. The many worlds interpretation takes a different approach. It says superpositions never collapse. Every possible measurement outcome occurs, but in different branches of reality. When you measure a quantum system, the universe splits into multiple versions, one for each possible result. You experience one outcome, but other versions of you in other branches experience the other outcomes. All possibilities are real, just in separate universes. Many worlds eliminates the measurement problem by eliminating collapse. There's no special boundary between quantum and classical. Everything is quantum, including observers. The universe is constantly branching into countless parallel realities containing all possible histories. This is mathematically clean, but ontologically extravagant. It multiplies entities beyond necessity, creating infinite universes to avoid one conceptual problem. Some physicists love it for its elegance. Others reject it as unfalsifiable metaphysics. You can never observe other branches, so how can you test whether they exist? Proponents argue the theory makes predictions about interference effects in quantum computing that distinguish it from Copenhagen. But these tests are subtle and controversial. Objective collapse theories propose that superpositions collapse spontaneously due to some physical mechanism, independent of observation. Perhaps gravity causes collapse when systems become massive enough. Perhaps there's a stochastic process in nature that randomly collapses wave functions. These theories modify quantum mechanics slightly to include collapse dynamics. They make testable predictions about where the collapse threshold occurs. Experiments are ongoing to test these proposals, but so far, quantum superpositions have been demonstrated for increasingly large systems, from individual atoms to molecules to microscopic objects. No evidence of spontaneous collapse has been found. The pilot wave theory, also called de Broglie-Bohm mechanics, keeps particles as real objects with definite positions at all times. The wave function guides the particle's motion like a pilot wave, but the particle is always somewhere specific. Measurement doesn't cause collapse. It just reveals where the particle already was. This interpretation is deterministic and removes the randomness of quantum mechanics, but it requires non-local connections where the wave function instantaneously affects particle motion across arbitrary distances. It also struggles with relativistic quantum field theory. Each interpretation has strengths and weaknesses. None are universally accepted. The choice between them is largely philosophical because they make identical predictions for all practical experiments. But the implications are wildly different. Are there parallel universes? Is reality fundamentally random or deterministic? Do observers play a special role in physics? We don't know. Quantum mechanics works perfectly for calculations, but we don't know what it means. This interpretational ambiguity affects how we think about cosmology. If many worlds is correct, the universe isn't just larger than we thought. It's infinitely larger, with every quantum event spawning new branches. The Big Bang didn't create one universe, but an ever-expanding tree of universes containing every possible history. If objective collapse is correct, then large quantum systems, like the early universe, might have behaved differently than small systems, affecting cosmic structure formation. If pilot waves are correct, the wave function of the entire universe is guiding cosmic evolution in deterministic but non-local ways we don't understand. The interpretation of quantum mechanics is not just abstract philosophy. It affects our understanding of cosmology, black holes, and the nature of existence itself. Let's return to observational anomalies. The lithium problem. Big Bang nucleosynthesis, the process that created light elements in the first few minutes after the Big Bang, makes precise predictions about the abundances of hydrogen, helium, and lithium. We can calculate exactly how much of each element should have been produced based on the density and temperature of the early universe. For hydrogen and helium, the predictions match observations beautifully. The universe contains about 75% hydrogen and 25% helium by mass, exactly as predicted. But lithium is wrong, specifically lithium-7. Big Bang nucleosynthesis predicts roughly 3 times more lithium-7 than we observe in the oldest stars. These metal-poor stars should have preserved the primordial lithium abundance because they formed before much stellar processing occurred. But they consistently show lithium deficits. Where did the lithium go? One possibility is that lithium was destroyed in stellar interiors and mixed to the surface, depleting the observed abundance. But lithium destruction requires specific temperature and mixing conditions, and it's unclear if all old stars would experience the right conditions to produce the observed uniform depletion. Another possibility is that our calculations of Big Bang nucleosynthesis are wrong. Perhaps the neutron lifetime or nuclear reaction rates are slightly different than we think. But these are well-measured quantities, and changing them enough to fix lithium would break the helium and hydrogen predictions. Some exotic solutions invoke new physics. Perhaps the universe contained additional particles during nucleosynthesis that affected lithium production. Perhaps dark matter interacted with normal matter during this epoch in ways that destroyed lithium. Perhaps the fundamental constants were slightly different in the early universe. All of these require adding new physics beyond the standard model. The lithium problem remains unsolved, a nagging discrepancy between prediction and observation that hints at something missing in our understanding of the early universe. While we're discussing elemental abundances, the origin of heavy elements presents puzzles. Elements heavier than iron can't be produced by normal stellar fusion because fusing iron consumes energy rather than releasing it. Heavy elements are created in explosive environments through rapid neutron capture. Supernovae and neutron star mergers are the suspected sites. But when astronomers model these events, the predicted abundances don't always match what we observe in the universe. Some elements, like gold and platinum, require very specific conditions to form. Neutron star mergers can produce them. But the rate of neutron star mergers might not be high enough to explain all the gold in the universe. We may be missing some production mechanism or underestimating merger rates. The R process, responsible for creating the heaviest elements, requires extreme neutron densities and temperatures. We think it occurs in neutron star mergers and some supernovae, but the exact astrophysical sites and conditions remain debated. Recent observations of gravitational waves from neutron star mergers have provided new data, confirming these events produce heavy elements. But quantitative predictions still have uncertainties. Another mystery is cosmic rays. These are high-energy particles, mostly protons, that constantly bombard Earth from space. They come from outside the solar system, accelerated to enormous energies by some mechanism. Most cosmic rays have energies similar to particle accelerators, and we think they're accelerated by supernova shockwaves. But some cosmic rays have energies far beyond anything we can produce artificially. Ultra-high energy cosmic rays have energies exceeding 10 to the 20 electron volts. That's macroscopic energy, the kinetic energy of a baseball, concentrated in a single proton. We have no idea how nature accelerates particles to these energies. Supernova shocks can't do it. Even the most powerful explosions fall short. Some theories invoke supermassive black holes, where particles are accelerated in the intense magnetic and gravitational fields near the event horizon. Others propose exotic sources like colliding galaxies or gamma-ray bursts. The problem is that ultra-high energy cosmic rays shouldn't be able to travel far. They interact with the cosmic microwave background through the GZK cutoff, producing pions and losing energy. Above a certain threshold, cosmic rays can only travel about 50 million light-years before losing too much energy to detect. So ultra-high energy cosmic rays must come from relatively nearby sources. But when we trace their trajectories back, they don't point to obvious sources. They seem to come from random directions with no clear origin. Some cosmic rays appear to come from voids, empty regions with no galaxies or energy sources. This makes no sense. Either our models of cosmic ray propagation are wrong, or the sources are obscured or exotic, or there's some acceleration mechanism in the voids themselves that we don't understand. Cosmic ray observations also hint at unexpected particle physics. The energy spectrum of cosmic rays shows features that don't match theoretical predictions perfectly. There might be additional particle species or interactions occurring at energies we can't reproduce in laboratories. Cosmic rays are natural particle physics experiments, probing energy regimes beyond human technology. They're telling us something, but we're not sure what. Let's discuss the axis of rotation of the universe more carefully. Beyond the axis of evil in the cosmic microwave background, there are other hints of large-scale alignment. Quasar polarization vectors, which indicate magnetic field orientations, show coherent alignment across gigaparsec scales. This shouldn't happen in a statistically isotropic universe. Magnetic fields in different regions should be independent and randomly oriented, but observations suggest otherwise. Some studies find alignments extending across billions of light-years. If confirmed, this indicates the universe has large-scale structure in magnetic fields, possibly related to primordial magnetic fields generated in the early universe. Primordial magnetism is poorly understood. We don't know if magnetic fields existed before the first stars, or how they would be generated. If large-scale magnetic fields thread the cosmic web, they could affect structure formation, cosmic ray propagation, and even galaxy formation. They might explain some of the anomalies we've discussed. But detecting and mapping primordial magnetic fields is extraordinarily difficult. They're incredibly weak and diffuse. Galaxy rotation axes also show some evidence of alignment in certain structures. Galaxies within filaments of the cosmic web tend to have their rotation axes aligned with the filament. This is expected from tidal torquing during structure formation. But some studies find alignments extending beyond what local tidal effects can explain, suggesting larger-scale coherence. These alignment anomalies could be statistical flukes. When you analyze millions of galaxies, you'll find some correlations by chance. But if they're real, They indicate the universe is not perfectly isotropic and homogeneous, even at very large scales. This would require rethinking the cosmological principle. Perhaps the universe only becomes truly isotropic at scales larger than our observable horizon. Perhaps there are relic structures from the pre-inflationary era that created preferred directions. Perhaps the universe has topology or rotation that we're only now beginning to detect. The cosmological principle has been a guiding assumption for a century. Challenging it would overturn fundamental cosmology, but observations might be forcing us to do exactly that. Now, let's confront something truly disturbing that we've danced around, but not fully addressed. The simulation hypothesis. The idea that our reality is a computer simulation created by an advanced civilization. This sounds like science fiction, but some serious physicists take it seriously. The argument is probabilistic. If it's possible to create high-fidelity simulations of reality, and if civilizations tend to create many such simulations, then simulated realities vastly outnumber base reality. There's one real universe, but potentially billions or trillions of simulated ones. Therefore, purely by probability, we're more likely to be in a simulation than in base reality. This assumes simulations are possible at sufficient fidelity to include conscious observers who can't tell they're simulated. We already create primitive simulations in video games and scientific models. If technology continues advancing, eventually simulations might become indistinguishable from reality to those inside them. The simulation hypothesis makes some testable predictions. Simulations might have computational limits that manifest as physical laws. The speed of light could be the maximum processing speed. Quantum mechanics might be a computational optimization where the universe doesn't render unobserved details. Glitches or artifacts might appear under extreme conditions. Some physicists have looked for evidence of pixelation in spacetime, arguing that if reality is simulated on a discrete computational grid, there might be a minimum length scale below which physics breaks down. The Planck length, about 10 to the minus 35 meters, is a candidate. Below this scale, quantum gravity effects dominate, and spacetime might not be continuous. Is this evidence of simulation, or just fundamental physics? We can't tell. The problem with the simulation hypothesis is it's unfalsifiable. Any observation can be explained as either real physics or simulated physics. If we find glitches, they're evidence of simulation. If we don't, the simulation is just very good. There's no experiment that definitively proves or disproves we're in a simulation. This makes it metaphysics, not science. Philosophically, the simulation hypothesis is equivalent to certain religious concepts. The simulators would be godlike entities who created our reality and could intervene or observe at will. We'd be dependent on their computational resources for existence. They could shut down the simulation at any moment. This is existentially unsettling, but operationally irrelevant. Whether we're simulated or real, we still need to eat, breathe, and understand the world we experience. The physics we discover applies to our level of reality, regardless of whether there's a deeper level beneath. So most physicists ignore the simulation hypothesis. It's entertaining speculation, but doesn't affect research. We study the universe as we observe it and assume it's real until proven otherwise. Let's return to concrete observational problems. The cosmic microwave background cold spot we discussed has a companion anomaly, the hemispherical asymmetry. When you analyze the temperature fluctuations in the cosmic microwave background across the entire sky, the statistics aren't quite uniform. Fluctuations in one hemisphere are slightly stronger than in the other. The asymmetry is small, only about 5 to 10% difference in amplitude, but it's statistically significant and confirmed by multiple satellite missions. In a perfectly isotropic universe, this shouldn't exist. Temperature fluctuations should have the same statistical properties in every direction. The fact that one hemisphere differs from the other implies a preferred direction in space. This is cosmologically heretical. One possible explanation is that we're observing residual effects from pre-inflationary physics. If inflation didn't completely erase all information about the universe before it occurred, there might be directional signatures left over. Perhaps the inflaton field had gradients or inhomogeneities that created preferred directions. But inflation is supposed to smooth everything out. That's its purpose. If it left directional signatures, it didn't do its job perfectly. Another possibility is we're seeing effects from superhorizon scales, regions of the universe larger than our observable horizon. If there are density variations or field values that vary across scales larger than we can observe, we'd see asymmetries because we're looking at a non-representative sample. This is observationally identical to living in a locally unusual region of a larger inhomogeneous universe. The hemispherical asymmetry might also be related to the axis of evil. They could be different manifestations of the same underlying phenomenon, some large-scale structure or alignment that affects the cosmic microwave background in multiple ways. Together, these anomalies suggest the universe is not statistically isotropic at the largest observable scales. Either our cosmological models are missing something, or we're seeing beyond the limits of standard cosmology into a realm where different physics applies. Now we should discuss what happens when you push general relativity to its limits. Naked singularities. General relativity predicts that when enough mass collapses into a small enough volume, it forms a singularity, a point of infinite density where space-time curvature becomes infinite and the equations break down. In black holes, singularities are hidden behind event horizons. You can't see them from outside. This is the cosmic censorship hypothesis, proposed by Roger Penrose. It states that singularities are always hidden and can never be observed directly. Nature enforces censorship, but the cosmic censorship hypothesis is a conjecture, not a proven theorem. Some solutions to Einstein's equations allow naked singularities, singularities without event horizons. If naked singularities exist, you could observe them directly. You'd see a region of spacetime where physics breaks down completely. Light could escape from the singularity, carrying information about conditions where general relativity fails. This would be incredibly useful for understanding quantum gravity, but it would also be catastrophic for predictability. Singularities are regions where anything can happen. If they're naked, the unpredictability infects the entire surrounding spacetime. You couldn't predict the future evolution of spacetime near a naked singularity because the singularity itself has no physical laws governing it. Fortunately, cosmic censorship seems to hold in realistic scenarios. When you simulate gravitational collapse numerically, event horizons always form before singularities become visible. Nature seems to conspire to hide singularities. But there are exotic situations where cosmic censorship might be violated. Rapidly rotating black holes approach extremality, where the event horizon shrinks and might disappear. Colliding black holes create complex dynamics where horizons merge and deform. Some theorists have found specific scenarios where naked singularities form temporarily before being clothed again by horizons. Whether stable naked singularities can exist remains unknown. If they do, we'd have observable windows into regions beyond physics. If they don't, there's some principle of nature we don't understand that prevents them. Either way, we're missing something. Another general relativity extremity is closed time-like curves. These are paths through spacetime that loop back on themselves in time. If you followed a closed time-like curve, you'd return to your own past. Time travel would be possible. General relativity allows closed time-like curves in certain spacetime geometries, particularly rotating universes or near-rotating black holes. The Gödel metric, a solution found by Kurt Gödel, describes a rotating universe filled with closed time-like curves everywhere. You could travel into your own past simply by journeying far enough in the right direction. Gödel presented this to Einstein, who was disturbed by the implication. If general relativity allows time travel, does that mean time travel is possible? Or does it mean something is wrong with general relativity? Most physicists believe closed time-like curves are unphysical. Quantum mechanics seems to forbid them through chronology protection mechanisms. If you tried to create a time machine, quantum fluctuations would become infinitely intense and destroy the mechanism before it could function. This is speculative, but supported by semi-classical calculations. The Novikov self-consistency principle proposes that even if time travel were possible, you couldn't change the past. Any actions you take in the past would be consistent with the history that already occurred. you'd be caught in a deterministic loop. This avoids grandfather paradoxes, but raises questions about free will and causality. The reality is, we don't know if time travel is possible because we don't have a theory of quantum gravity. General relativity allows it in principle. Quantum mechanics seems to forbid it. Until we unify them, we can't definitively answer whether closed time-like curves exist in nature. Let's discuss one final mystery that encompasses many others: the arrow of time. Time flows forward. We remember the past, not the future. Entropy increases. Eggs break but don't spontaneously reassemble. This seems obvious, but physics doesn't explain why. The fundamental laws of physics are time-symmetric. If you reverse time in the equations of motion, they still work. A movie of particles colliding, played backward, still obeys the laws of physics. And yet, the universe clearly has a directionality to time. This is the arrow of time problem. Thermodynamics provides a partial answer. The second law states that entropy, disorder, increases over time. This gives time a direction. The future is the direction of higher entropy. But why? Why does entropy increase? The statistical mechanics answer is that high entropy states are more probable than low entropy states. There are more ways for things to be disordered than ordered. So systems naturally evolve toward higher entropy. But this just pushes the question back. Why did the universe start in a low entropy state? The Big Bang was an incredibly ordered, low entropy configuration. All matter and energy concentrated in a tiny volume. If the universe began in thermal equilibrium, maximum entropy, nothing would happen. Time would be meaningless. The fact that we have an arrow of time means the universe began far from equilibrium. Why? We don't know. The initial conditions of the Big Bang are simply assumed. Some cosmologists propose that inflation created low entropy initial conditions by stretching quantum fluctuations into classical density variations. But this doesn't explain why inflation itself occurred, or why the pre-inflationary state was conducive to inflation. You're just moving the mystery earlier. Others invoke cyclic cosmology, where the universe goes through repeated cycles of expansion and contraction. At the end of each cycle, entropy is somehow reset, allowing the next cycle to begin with low entropy. But this requires exotic physics and violates thermodynamics, unless there's some mechanism to dump entropy out of the universe. Roger Penrose's conformal cyclic cosmology attempts this by proposing that in the infinite future, when all matter has decayed and only massless particles remain, the universe loses all sense of scale. In this state, the universe can be conformally mapped to a new Big Bang, restarting with low entropy. This is mathematically elegant, but speculative. The arrow of time might also be connected to quantum mechanics. Wave function collapse is irreversible, and time asymmetric. Measurement destroys superpositions and increases entropy. Perhaps the quantum measurement process is the source of the time arrow. But this requires solving the measurement problem, which, as we discussed, remains unsolved. The arrow of time is deeply mysterious because it's so fundamental and yet unexplained. We experience time flowing forward. We build our entire understanding of causality and change around it. But we don't know why time has an arrow, or what set the initial conditions that created it. This is one of the deepest questions in physics. Now we must confront where all of this leaves us. We've cataloged dozens of anomalies, mysteries, and contradictions. The universe is expanding at an accelerating rate driven by energy we don't understand. It's filled with matter we can't detect. It contains structures too large to exist in the time available. It has temperature anomalies and alignments that violate isotropy. It's missing lithium, contains rogue planets, and might be rotating. Black holes that grew too fast. Stars that are too old. Cosmic rays with impossible energies. Constants that might not be constant. Quantum mechanics and gravity that can't be unified. Information paradoxes. Naked singularities. Time travel possibilities. The arrow of time itself unexplained. Every direction we look, we find things that don't fit the models. Does this mean physics is broken? No. It means physics is incomplete. Science progresses by finding anomalies and resolving them. Every mystery we've discussed represents an opportunity. a crack in our understanding where new physics might enter. The history of science is a history of paradigm shifts. Newtonian mechanics worked perfectly until it didn't. Mercury's orbit precessed wrong. Relativity emerged to fix it. Classical physics explained everything until blackbody radiation and the photoelectric effect demanded quantum mechanics. The Standard Model explained particle physics until neutrino oscillations required neutrino mass. Every time we find something wrong, we build a deeper theory. We're currently in a pre-paradigm shift state. The anomalies are piling up. The Standard Model of cosmology, lambda CDM, fits most of the data but has cracks. The Hubble tension, the JWST galaxies, the large structures, the lithium problem. Dark matter and dark energy remain completely mysterious despite decades of searching. We've parameterized our ignorance by naming it, but we haven't explained it. Something is missing. Maybe it's new physics beyond the Standard Model. New particles, new forces, new symmetries. Maybe it's modifications to gravity at cosmic scales. Maybe it's quantum gravity effects bleeding into cosmology. Maybe it's exotic topology or extra dimensions. Maybe it's something we haven't imagined yet. The next breakthrough might come from any direction. A particle detection that finally reveals dark matter. Gravitational wave observations that test strong field gravity. Quantum computing that enables calculations currently impossible. Astronomical surveys that map the universe in unprecedented detail. Or a theoretical insight that reorganizes everything we know into a deeper framework. What's certain is that the universe is telling us we're missing something fundamental. The anomalies aren't going away. They're multiplying as our observations improve. We're in the uncomfortable position of knowing that our best theories are incomplete, but not knowing how to fix them. This is simultaneously frustrating and exhilarating. Frustrating because we can't answer basic questions about what constitutes most of the universe. Exhilarating because we're living through a period where fundamental discoveries are possible. We stand at the edge of knowledge. Behind us, a century of progress that revealed the Big Bang, quantum mechanics, relativity, the Standard Model of particles, cosmic acceleration. Ahead of us, darkness and mystery. 95% of the universe unknown. The fundamental laws incomplete. The deepest questions unanswered. Some people find this terrifying. The universe is stranger and more incomprehensible than we imagined. We're small and ignorant, floating in a cosmos we don't understand. But there's another way to look at it. We have the privilege of living in an era where we can ask these questions and possibly answer them. We have telescopes that can see the edge of the observable universe, particle accelerators that recreate conditions from the Big Bang, gravitational wave detectors that hear black holes colliding, quantum computers beginning to simulate reality itself. We're not ignorant because we're primitive. We're ignorant because we've learned enough to recognize how much we don't know. That's progress. 1,000 years ago, people didn't know what they didn't know. Today, we can articulate precise questions. What is dark matter? What is dark energy? How do you unify quantum mechanics and gravity? What set the initial conditions of the Big Bang? Why does time have an arrow? These are well-formed questions that might have answers. We just need to find them. The universe isn't obligated to make sense to us. We're pattern-seeking primates who evolved to avoid predators and find food, not to understand quantum field theory or cosmic expansion. The fact that we can understand anything at all is remarkable. The fact that mathematics, invented by human minds, describes physical reality with extraordinary precision is deeply mysterious. Why should the universe be mathematical? Why should it follow laws we can discover? We don't know, but it does, and we can, and that's a profound gift. So yes, nothing makes sense anymore. The comfortable certainties of 20th century physics have dissolved into quantum foam and dark sectors, and accelerating expansion. The universe is weirder than we thought, but that's not a failure. That's an invitation. Every mystery is a door. Behind some of these doors might be the most profound discoveries in human history. The nature of matter and energy, the origin and fate of the universe, the possibility of other realities. the fundamental structure of existence itself. We don't know what we'll find. We might discover that dark matter is an entirely new sector of particles with its own forces and complexity. We might find that dark energy is a dynamic field that will tear the universe apart or collapse it. We might unify physics into a theory of everything that explains all forces and particles from a single principle. Or we might find that some questions have no answers, that Gödel's incompleteness applies to physics itself, and certain truths are forever beyond our reach. Either way, the search is worthwhile. Understanding the universe is a fundamentally human endeavor. We look up at the stars and ask why. We've been doing this for thousands of years, and we'll keep doing it as long as we exist. The mysteries we face today are the inheritance of everyone who came before us and asked the same question. And the answers we find, if we find them, will be our legacy to everyone who comes after. The universe is vast and strange and filled with things that shouldn't exist. The cold spot that might be a scar from another universe. The dark flow pulling galaxies towards something beyond our horizon. The structures too large for the timeline. The energy emerging from nothing. The matter we cannot see. The constants that might be changing. The singularities hidden and naked. The time that flows but shouldn't. All of it defies our expectations, because our expectations were built on incomplete knowledge. We're updating our expectations. We're learning to be comfortable with mystery while simultaneously working to resolve it. We're accepting that the universe is under no obligation to be simple or intuitive, while still believing we can understand it piece by piece. This is the scientific mindset. Humility combined with ambition. We admit ignorance while refusing to accept it as permanent. We catalog what we don't know, and then we go find out. So when you look up at the night sky tonight, don't just see points of light. See the cosmic microwave background filling space with ancient photons that carry messages we're still learning to read. See the dark matter flowing invisibly between galaxies, holding everything together with gravity we can measure, but not explain. See the dark energy pushing everything apart, accelerating expansion toward an unknowable future. See the structures too vast to exist, the galaxies too early to have formed, the black holes too massive to have grown. See the unanswered questions hanging in the void, and recognize that you're looking at the frontier of human knowledge. Everything beyond that frontier is mystery. Everything within it was mystery once too, until someone looked closely enough and thought deeply enough to understand. We're standing on the shoulders of giants who looked at mysteries and solved them. Now we face new mysteries. Harder ones, deeper ones. Mysteries that might require new mathematics, new physics, new ways of thinking. But there are mysteries, our generation's inheritance and challenge. Nothing makes sense anymore because we've learned enough to realize how little we knew. The universe has revealed itself to be stranger than we imagined, and probably stranger than we can imagine. But that strangeness is real. It's there, in the data, in the observations, in the contradictions we can't ignore. And somewhere in that strangeness is the truth. The actual nature of reality, waiting to be discovered. We might be decades away from the breakthrough. We might be centuries away. But the fact that mysteries exist means answers exist too. The universe has secrets, but it's not keeping them out of spite. It's just vast and complex, and operating on principles we haven't fully grasped yet. Every civilization that came before us looked at the sky and saw mystery. Most accepted it as divine, unknowable, beyond human comprehension. We're the first who refused to accept that answer. We built telescopes and particle accelerators and gravitational wave detectors. We launched satellites and probes and rovers. We developed mathematics sophisticated enough to describe quantum fields and curved spacetime. We're not content with mystery. We're using mystery as a map to guide us toward truth. So yes, nothing makes sense anymore. The universe is broken. Or our understanding is, and we're trying to figure out which. The anomalies are everywhere, the contradictions mounting, the frontier of knowledge marked by confusion and awe. But confusion is the price of discovery. Awe is the reward for looking closely. And the understanding we build from these mysteries, when we finally achieve it, will be the most hard-won and precious knowledge humanity has ever gained. We're living in an age of cosmic confusion, an era where the universe is actively defying our best attempts to understand it, where every new observation seems to make things worse instead of better, where the more we learn, the less we seem to know. This is uncomfortable. This is frustrating. This is exactly where we need to be. Because the only way out is through. The only way to resolve these mysteries is to face them, document them, study them, test hypotheses, build better instruments, think harder. The universe isn't going to make it easy. It never has. But it does leave clues. And humans are very good at following clues. We've gone from thinking the universe was a few thousand years old and geocentric, to measuring its age at 13.8 billion years and understanding its expansion. We've gone from thinking atoms were indivisible, to splitting them and discovering quarks. We've gone from thinking light was a wave or a particle, to accepting it's both, and neither depending on how you look. We've adapted before. We'll adapt again. The paradigm will shift. The mysteries will resolve into new physics. And that new physics will reveal new mysteries deeper still. This is the pattern. This has always been the pattern. Knowledge doesn't end mystery. It transforms mystery into understanding, which reveals new mystery. It's an infinite recursion. We'll never reach the bottom, because there might not be a bottom. But every level we descend, we understand more. We see further. We grasp deeper truths. So stand at the edge of knowledge and look out into the darkness. See the anomalies, the contradictions, the things that make no sense. Don't look away. Don't pretend they're not there. Don't settle for comfortable ignorance. Look directly at the mystery and ask why. That's what scientists do. That's what humans do. We see something that doesn't make sense, and we can't let it go. We need to know. We need to understand. It's a compulsion written into our nature. The same curiosity that made us wonder what's over the next hill now makes us wonder what's beyond the cosmic horizon. The same drive that made us tame fire now makes us smash protons together at near light speed. We're explorers. It's who we are. The territory has changed from physical space to conceptual space, from new lands to new physics. But the exploration continues, and the frontier is vast, infinite perhaps. So nothing makes sense anymore. Good. That means there's still work to do, still mysteries to solve, still understanding to be won from the chaos. The universe is strange, and we are small, but we're not defeated. We're curious. We're determined. And we're just getting started.